Hello and welcome. In this video, we're going to talk about what the interval of convergence is and what the radius of convergence is for a power series and how to find the interval or radius of convergence of a given power series. So let's go ahead and jump right in. Okay, before we jump into interval and radius of convergence, I want you to look at this series here, the sum from n equals 0 to infinity of x over 3 to the power of n. And I want you to think about for what values could we plug in to x that would give us a series that's going to converge. So let's think about what we know about this particular series. If x was just a number, then this would be a geometric series. And we know that a geometric series is going to converge when the absolute value of the ratio is less than 1. So let's just plug in what our ratio is. In this case, x is in our mind holding the place of some number. So the absolute value of x minus 3 would be less than 1. And to solve this inequality, we could break this up to get rid of the absolute value. And then to finish it off, we could multiply both sides, or all sides, by 3. So as long as we have an x value that is in between -3 and +3, we will have a series that converges. So all x, that's an element of -3 to +3, will create a series that converges. Because of the geometric series test. So if we plug in 1, we'd have 1/3 to the power of n. That's going to converge by the geometric series test. If we plugged in 4, which would be outside that interval, that would diverge by the geometric series test. So this idea of having a variable inside our rule, not just n, which is the value that's changing, but actually adding together terms that contain a variable, is going to lead us to a new idea, and that idea is a power series. So let's go ahead and define what a power series is and then talk about how we're going to use a power series specifically in this section to talk about the interval and radius of convergence. A power series is an infinite series whose pieces are expressions in terms of a variable with an increasing power. So it's sort of like a polynomial, except we can't really call it a polynomial because it's going on forever, which polynomials are defined to have a finite degree, which in this case it would not. But you can think about it like a polynomial. So this is the general form for a power series, and we're going to focus a lot on power series in the next couple of sections. This particular power series is centered at some value c. And what we're going to do in this section is we're going to talk about over which values does a particular power series converge, right? Because as we just saw with that last example, there are x values that we could plug in that would make this series converge, and there are x values that we could plug in that would make the series diverge. And those values, or that interval, which for the last problem we talked about that interval being from -3 to 3, this interval has a special name. It's called the interval of convergence, and it's often abbreviated IOC. So the interval of convergence is the interval that contains all of the x values that will permit the series to converge. So we just found the interval of convergence for that last geometric series, but we're going to talk about how to find the interval of convergence for any series. And the easiest way to do that is to actually start by using the ratio test. So in order to determine the interval of convergence, we need to consider what would make the ratio less than 1, just like we did with the ratio test. So for each problem where we are finding the interval of convergence, we're going to perform the ratio test. Our final ratio will be the absolute value of something that still contains x, and we need that absolute value statement to be less than 1 in order for this to converge. So then we can set up an inequality, whatever our x portion was. We can set up an inequality and solve for x in the middle in order to figure out for what values it will converge. One thing that we need to consider, though, is that it is possible that we could have convergence at the endpoints. So we actually need to perform the ratio test to find the interval of convergence, and the endpoints will create two unique series, and we have to test each of those series for convergence to see if they are included or not included in our final interval of convergence. So, step 1, perform the ratio test to identify the interval of convergence. Step 2, solve that absolute value statement to figure out what the interval is going to be. Step 3, create a series with each of those endpoints and test to see if that series converges or diverges so that you can finalize that interval. So let's walk through this together. Let's first perform the ratio test. So go ahead and pause the video and perform the ratio test on this series here. So first, we're going to set up the limit as n approaches infinity of our ratio, which is a sub n plus 1 over a sub n. Now we're going to simplify anything that simplifies. So remember that we're substituting n plus 1 in for our n's, not for our x values. So if we simplify this, this is going to be the limit as n goes to infinity of the absolute value of, well, this x minus 5 to the power of n and this x minus 5 to the power of n are going to go away. So we just have x minus 5 to the first power in the numerator here. This 3 to the n and 3 to the n plus 1 is going to leave us with just a 3 in the denominator. And then in the numerator we have an n, and in the denominator we have an n plus 1. So the absolute value of that, as n goes to infinity, these two n values are changing at the same rate, so we are just going to be left with the absolute value of x minus 5 over 3. And what we need for our interval convergence is for this to be less than 1. So let's go ahead and set up this absolute value statement. -1 is less than x minus 5 over 3 is less than 1. Multiply everything by 3. And then add 5, so that's going to give me 2 is less than x is less than, oops, I didn't make this a 3. 5 plus 3 is 8. So step 1 was perform the ratio test. Step 2, in light blue here, is setting up your interval, and step 3 is going to be to create two series to check the endpoints. So I'm going to say let x equal 2. I need to figure out if this inequality should have an or equal to symbol under it, because if this series works and converges when x is equal to 2, then that should be less than or equal to, greater than or equal to. So let's see what happens when x equals 2. If x equals 2, we have the series from 1 to infinity. 2 minus 5 is going to be -3 to the power of n over n times 3 to the power of n. And this series can be simplified. The 3's are -3 to the n and 3 to the n can divide to just be -1 to the n over n. This is the alternating harmonic series, which we know converges. So I'm going to come up here and I'm going to add an or equal to symbol under the inequality by 2, because this series converges if x is equal to 2. Well, now let's consider our other option. Let's let x equal 8. So then we would have the sum from n equals 1 to infinity. 8 minus 5 is going to be 3, so 3 to the n over n times 3 to the n. That's going to simplify. This is the sum from n equals 1 to infinity of 1 over n, which diverges since it's harmonic. That means no or equal to here. So we can say, now that we have performed the ratio test, that we have found our inequality statement and tested our endpoints, we can say, therefore, the interval of convergence is 2 less than or equal to x less than 8. So again, we're performing the ratio test. We're setting up our inequality to solve our absolute value statement. And then we're checking each series that is formed by the endpoint of the interval to see whether or not they are included in our interval of convergence. Let's work through a couple more examples. Okay, step 1, perform the ratio test. So go ahead and pause the video and walk through the ratio test on number 1. So here, after we perform the ratio test, this is going to simplify down to just be as n goes to infinity. This is 1 times x minus 3, so the absolute value of minus 3. We need that to be less than 1. So this was x, absolute value of x minus 3. We need that to be less than 1 in order for this to converge. So we're looking at this inequality, and if I add 3 to both sides, 2 is less than x is less than 4. Now we need to check our endpoints. So I'm going to let x equal 2. That's going to give me the sum from n equals 1 to infinity of negative 1 to the n over n, which is the alternating harmonic series and is going to converge. So I can add an or equal to here. And then I'm going to let x equal 4. If I plug 4 in, wow, I'm having deja vu from the problem that we just did. This is going to become 1 over n, which diverges because it's the harmonic series. So our interval of convergence is going to be 2 is less than or equal to x is less than 4. And you can write that in interval notation or using inequalities. Let's look at number 2, and I'm going to clean this up and make some more space for it. So if you need to get anything down from number 1, go ahead and pause the video, and I'm going to clear out some space for us. Okay, go ahead and perform the ratio test and see if you can get all the way to the interval without having done the specific tests for the endpoints. Then unpause the video and see how you did. So you may or may not have noticed on this series that since these are both to the power of n, you can actually combine them to be negative 3x inside. That just meant that I got to do a little bit less writing here. This is going to have, as n goes to infinity, this is going to be 1, so we're just left with negative 3x. We need that to be less than 1, or we need the absolute value of that to be less than 1. And since absolute value makes it positive, we can just change it to be 3x. So we're looking at the inequality, negative 1 is less than 3x is less than 1, and then we're multiplying everything by, dividing everything by 3 to get that value. Now we need to check the endpoints. So if we let x equal negative 1/3, then our series is going to become the series from n equals 0. If I plug negative 1/3 in here, I can multiply those two things together, which is just going to give me positive 1 over the square root of n plus 1. Now this series is going to diverge, but you have to still prove that it diverges. And the best way to prove that this diverges is using the comparison test. So I need to define a new series, so I'm going to say consider the sum from n equals 1 to infinity of 1 over the square root of n, which diverges by the p-series test, since p is equal to 1/2, which is less than 1. Now, I'm going to use limit comparison, so I'm going to take the limit as n approaches infinity of 1 over the square root of n plus 1 times the square root of n, which is 1, which is greater than 0. Therefore, I'm going to come over here and call this a. Therefore, a diverges by LCT, since, and I'm going to call this one b, b diverges. So I am not going to have an or equal to symbol here. That series diverged. But I still need to check what's happening at positive 1/3. So let x equal positive 1/3. Then we have the series from n equals 0 to infinity of negative 1 to the n over the square root of n plus 1. This is an alternating series. It looks like it might converge using the alternating series test, but let's go ahead and confirm. The limit as n approaches infinity of 1 over the square root of n plus 1 is 0. Based on the way the denominators are behaving, a sub n plus 1 is less than or equal to a sub n. Therefore, I'm going to call this C. C converges by AST, which means, therefore, our interval of convergence is going to be negative 1/3 is less than x is less than or equal to positive 1/3. Now, you might be asking yourself, does it always just work for one of them? Is there ever a case where both of them work? Is there ever a case where neither of them work? And the answer to that question is yes, all of those things are possible. It could be that they are both closed, both ends of the interval are closed. It could be that they're both open, and it could be one of each. Each individual series needs to be tested so that you can identify what that overall interval of convergence is going to be. Let's do 2 more examples on interval of convergence, and then we'll talk about radius of convergence. Okay, I'm going to encourage you to pause the video and work through both of these problems on your own, and then unpause the video and see how you did. So here are both of those problems with the ratio test performed and identifying the interval. So here I need to check -1 and 1 for number 3. And on number 4, let's make that a little bit more clear, less than 2x less than 1, I'm going to need to check positive and -1/2. So go ahead and perform each test. Let x equal 1 and -1 for number 3, and let x equal -1/2 and +1/2 for number 4, and then find the full interval of convergence. So if x is 1, I'm not sure why I started with 1 and not -1, but if x is 1, we get the sum from n equals 1 to infinity of 1 over 2n minus 1, which you can perform a comparison test to the harmonic series to show that it diverges. So it will not be included in our interval. And then if you let x equal -1, you get a series that you can perform the alternating series test on to show that it converges. Therefore, our interval of convergence is going to be -1 less than or equal to x less than 1. If you haven't already worked through number 4, I encourage you to pause it and work through the rest of it, and then unpause the video and see how you did. So this problem works out pretty nicely. If you plug in -1/2, you end up with a p-series, 1 over n squared, which converges by the p-series test. If you plug in +1/2, you end up with an alternating series that's going to converge by the alternating series test. So this time we have the interval from -1/2 to +1/2, and it's inclusive on both sides. Now that we've talked about the full interval over which a series can converge, a power series, a series that has an x component within it, let's talk about just almost scaling back a little bit and just talking about the length over which a series can converge. And that's going to lead us to the idea of the radius of convergence. So the interval of convergence gives us all of the x values, or the interval over which the interval that contains all of the x values for which a particular power series will converge. The radius of convergence, on the other hand, is simply the distance from the center of the interval to an endpoint at which its convergence ends. So if we knew, thinking about that last example, if we knew that the interval of convergence was this, we could say that the radius of convergence, r, is the distance from the center, 0, out to 1/2. So the radius of convergence for this particular power series, looking back at number 4, the radius of convergence would be 1/2, the distance from the center to either endpoint in either direction. So not the full length, that would be the diameter. The radius is the distance from the center to the endpoint. So really, you can just think of it as the radius will be half the length of the interval of convergence. A couple things to note: every power series converges at least its center. So if x was equal to c, then we would have 0. Any series that it just becomes 0 plus 0 plus 0 an infinite number of times is going to converge to be 0. So we can look at the particular values, how far we are from the center, to think about what our r value is. So let's consider the power series below. Let's go ahead and use the ratio test to identify what we would need for the interval of convergence. So go ahead and perform the ratio test on that example there. So if we take the limit as n goes to infinity here, we're going to end up with n times x. Since the numerator, this is an increasing series, this limit is going to be infinite, which means that the radius of convergence is going to be 0, because the only place this series will converge is at the center. So this series from n equals 0 to infinity of n factorial times x to the end will only converge when x equals 0, which is at the center. Because if x is 0, then we're adding 0 together an infinite number of times, and that will always converge. Let's look at some more examples where the radius is bigger than nothing. Those are definitely more interesting cases, and let's work through this process. So that the steps that we're taking is are similar to what we just did with the interval of convergence, except that we don't actually have to test the endpoints because our ultimate goal isn't to find an interval, it's to find the length of the radius, which means we can stop as soon as we get to a point where we can tell what that length is going to be. So let's set up some more examples here. All right, so step one, let's perform the ratio test. So we're going to set up our limit. This is going to be equal to the absolute value of 4x as n goes to infinity. We need this to be less than 1. So -1 is less than 4. X is less than 1. So -1/4 is less than x is less than 1. This is centered at 0. Since there's no x minus quantity, which would make it centered somewhere else. How far is it from 0 to 1/4? Well, that is a length of 1/4. So our radius of convergence is 1/4. The distance from the center, which in this case is 0, to the outside interval in either direction. So if you look at number 6 is centered at x equals -4. So we're going to be looking at how far our interval is, how far in each direction from -4. So ratio test first, go ahead and do that part. That's going to end up giving us the absolute value of x plus 4 over 3. So now we can set up our inequality because we need this to be less than 1. -1 is less than x plus 4 over 3 is less than 1. -3 is less than x plus 4 is less than +3. And if I subtract 4 here, so how far is it from x to -1? And remember, we're talking about the center being at -4, so half that distance. The distance from -4 to -1 or from -4 to -7 would give us our radius, which is 3. The other way that you can think about it is the total distance from -7 to -1 is 6, and half of that total length would be 3. Whatever way is easier for you to think about it, go about it in that way. Okay, let's look at 2 more examples like this, and then let's look at a more abstract example, and then we will be done. All right, I'm going to encourage you to work through these 2 problems on your own and then unpause the video and see how you did. For number 7, this limit is going to be infinite since we're going to have n to the 4th over n to the 3rd, which you could probably have seen that over here. This is an increasing series. N factorial is growing faster than that denominator, which means this series will only converge at the center. So the length of the radius would be 0. This only converges if x equals 0. All right, go ahead and work through 8. So by the ratio test, and you don't have to say that, but I think it makes it clear what you're doing. And again, you want to be writing this out so that someone else can follow what you're doing. You're going to get that this limit is just the absolute value of x, which we need to be between 1 and -1. So the length from the center, which was 0, to the end is going to be 1. The radius of convergence is going to be 1. Okay, let's take this to the next level and look at an example that is more abstract, and then we will wrap up. Here we go. The power series below, the power series over here, is known to converge when x equals -2 and to diverge when x equals 5. And then we're going to be asked some questions about it. So notice that it is centered at x equals 0. And I know that it's centered at x equals 0 because it's not x minus some number to the power of n, it's just x. So that means it's centered at 0. What is the smallest possible radius of convergence? Well, if we know that it converges at -2, the distance from the center 0 to -2 would be +2, or with the length, the distance, right? The radius could be 2. And this is the answer to the question, but what I want you to think about is we could be saying -2 is less than x is less than 2. We know for sure it converges there. We don't know what's happening at +2 because as we saw with the interval of convergence earlier in this video, it could have an or equal to symbol at one end of the interval, but not at both. So the smallest radius would be length 2. The largest radius could be, we know it diverges at +5, but it could converge at -5, right? We know for sure that there is no or equal to here, but we don't know what's happening here. So the largest possible length it could be is 5, and that would only be if there was an or equal to symbol here. We can't conclude for sure that there's not, so the largest possible radius would be 5. This last question is going to ask us to look at a bunch of different values based on this given information. So -8, -5, -1, 1, 2, and 4. And we're going to be asked, does it converge or diverge, or do we not know? So based on what we just saw, if we know for sure that it diverges at +5, for sure it diverges at +5, that means it can't go more than 5 away from the center, which automatically means that -8, which is more than 5 away from 0, it's going to diverge at -8. It's not possible for it to converge there. We already talked about how just because it diverges at +5 doesn't mean it diverges at -5, so we don't have enough information to conclude what's happening at -5. At -1, we know it converges. We know the minimum radius is 2, so could we go out -1? Absolutely. It's definitely going to converge when x is equal to -1. Similarly, it's going to converge when it's equal to +1 because we know that the smallest this interval could be is what we have right here in A. We don't know what's happening at 2, so we're going to just put a question mark there. It could converge there. It could diverge there. We don't know. And we don't know what's happening at 4 because the only other piece of information that we know is that it's diverging at 5, but it could be converging at 4. So based on the information that we're given, we know how far away from the center we could be going at most and at least, and we can draw conclusions based on that information. So in this video, we talked about finding the interval of convergence using the ratio test, figuring out what values make a power series converge or diverge. Then we talked about the length of half of that interval or the radius of convergence and how to identify that, also using the ratio test. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.